just so I know who I'm talking to, and I recognize most of you from quantum mechanics class, so that makes it easier. But who here has not taken quantum mechanics? Okay. Who here has not taken E&M, electricity and magnetism? Okay. You will have to take my word for a few things, and just trust me on that. I'm going to mostly start with the very, very general stuff. I do think we should get into a little bit more of the quantum specifics so that the people who have already been taking some quantum will understand a bit more. But hopefully I can give enough introduction that it'll be understandable for everybody. So the basic idea here is if you have a quantum two-state system, a qubit, when you perform a measurement of what state it's in, you only get two possible values. So typically we say that these values are 0. Oh, this is a great time for my tablet to decide not to work. Okay, I need to restart this. one second. I will restart that computer and I'll just talk about it for a little while with that drawing. So anytime you have a measurement in quantum mechanics, there are certain quantities you can measure that only come out with quantized values. So those of you who haven't taken quantum, did you ever take any chemistry in high school? Yeah? So you learned about atomic orbitals, right? So atomic orbitals are really just the different energies that electrons can have when they're in a bound state around a nucleus. And the key is that they're quantized. They can be in orbital 1s or orbital 2p, but they can't be anywhere in between. The state is known, it's a quantized thing. The simplest example of this is a quantum system where there's only two possible states. Like a coin flip, it could be heads or it can be tails. Classically, this is something we would represent as a 0 or a 1. So we'd classically represent it as a bit. Well, in quantum mechanics, we have the same thing. It's a quantum bit, so we call it a qubit. And again, it's just a two-state system. Those of you who have taken quantum, we typically use the math of spin 1/2 to describe it. But it really doesn't have to represent any specific physical thing. It's just any system that has two states. Now, the cool thing about quantum mechanics is that you don't just have to pick one of these states to put the system in. You can put the system in a superposition of these states. You can basically say it's like 20% in state A and 80% in state B, or some combination there like that. Now, this sounds really weird physically, but the math of it is actually really simple. You've all seen vectors before. And you've probably all added vectors before. I can take one vector that's pointing this way and another vector that's pointing this way, and I add them together, and I get a vector pointing this way. And depending on how much of each of these I add, I get a vector pointing sort of anywhere in between. You can do that with quantum mechanics. And in fact, the language of linear algebra, of vectors, is how you do it. But what's interesting about quantum mechanics is that if you go to try to measure, hey, what direction was my vector pointing in? You only get one of the original answers. You only get this way or this way. So, okay, I talked about that as vectors, but when they're states, basically, sorry, I'm getting my tablet back in here. Brenda, can you let me in? Okay. So when they're states, we typically write them in this kind of notation, like there was a state 0 and a state 1. And we can basically add them together with some coefficient, a times 0 times plus b times 1, to get some arbitrary state, which I'll write as a Greek letter psi. Now, this is a definite thing. We know this state. But when we go to measure what state is in it, we only get back 0 or 1. And this is how measurements are taught. But it's actually not exactly correct physically, because measurement isn't like a discrete process. It takes a little bit of time. Somehow you have to get a signal onto your experimental, apparatus, and you need to integrate that signal for a little while. You need it to exist for longer than 0 time in order for you to see it. And what this means is that the measurement's sort of taking place over this time. So the qubit starts out in this superposition state, starts out like this, and then it ends up in the state 0, or it ends up in the state 1. It turns out that the probability that it ends up in the state 0 is the modulus square of that coefficient a. The probability of ending in 1 is the modulus square of this coefficient b. So the question then is, there's a question you can ask, which is, what happens if I only measure it a little bit? In other words, what happens if I start my measurement, but then I stop it in a really short amount of time? Or I measure very weakly in some way, so that I don't really get enough information out to determine whether the system is in 0 or 1. What ends up happening is that you get measurement results that kind of make it more likely to be in 0 or more likely to be in 1, but not certain. And this actually kicks the system towards 0 or towards 1. So there's the simplest way, I think, is just to jump into how this actually works in this particular physical system. So in this particular physical system, they take what's called a superconducting qubit. It's basically a electrical circuit made up of superconductor that you can get to have 2 states. And they put it inside a resonant cavity. It's basically a box that effectively is like a mirror for light, for electromagnetic radiation at a certain frequency. In this case, it's about 6 gigahertz. And they engineer an interaction in such a way that this resonant cavity, which is basically like a harmonic oscillator. Okay, resonant cavity has a resonant frequency. It responds most strongly at a certain frequency of drive. Just like a mass on a spring responds most strongly when you drive it right at its natural frequency. What you can do if you take this cavity and you put your 2-state system inside of it, is you can engineer an interaction so that the resonant frequency of the cavity depends on the state of the qubit. So one way to think about it is like, let's say your qubit, this is a really funky example. But let's say you had a mass on a spring. And then you had another spring here that was kind of small that could attach to it. And in one state, your qubit made this spring attach, and in the other state, your qubit let that spring detach. Well, the mass would oscillate differently. Now, the way we see this is we actually take this cavity and we send in an electromagnetic wave, we send in light, and either it transmits through or it reflects back. In this particular case, they were looking at something that reflected back. It reflects back, and when it reflects back, this wave, which has a phase, it has a certain part of the oscillation that it's in at a certain time, that phase shifts. Basically, the light coming back acts like it's been delayed by a certain amount, by a certain time. And that amount of delay depends on the difference of the frequency of the probe, omega probe, and the frequency of the cavity, omega c. But the cavity frequency is a function of the qubit state. So what you have here is a phase shift, delta phi, which is a function of the difference between the cavity frequency and the probe frequency. And the cavity frequency is a function of the qubit state. Sorry. And so by measuring this phase shift, you can measure the qubit state. Now, I said this doesn't happen all at once, and there's a fundamental reason why. Y'all have heard of the uncertainty principle, even if you haven't taken quantum mechanics? The uncertainty principle, commonly said, is you can't know the position and momentum of a particle at the same time. That's not actually exactly correct. It's that the particle doesn't have a position and momentum at the same time. They are not well defined. If you are in a state of definite position, you are in a superposition of different momentum states and vice versa. Now, it turns out that the light that you send in doesn't actually have a definite phase. Basically, the light is something that goes like cosine omega t plus something that goes like sine omega t. And there's some uncertainty in the relative amplitudes of those two terms. Those two terms are kind of like position and momentum. You can't specify them both at the same time. So what this actually looks like, and I have lost the paper. Hold on, let me pull that up. I'm going to show you what this looks like in the paper. It's got to be easier to just paste this into my OneNote than it is to keep switching back and forth. What this looks like is this. So y'all can see this, right? These axes here, I and Q, are basically the amplitudes of the part of the light that goes like sine omega t and the part that goes like cosine omega t. When the phase of the light shifts, those relative amplitudes shift. Basically, like this vector goes around in a circle. You know, a cosine is just a sine that's been phase shifted by 90 degrees. So you just change this vector around. Now, classically, I could say like, okay, my signal is this much cosine omega t and this much sine omega t. And so here's the vector in IQ space that represents my signal. But quantum mechanically, these two things are fundamentally uncertain. The amplitude of the sine omega t term and the cosine omega t term cannot be determined at the same time. And so what you end up with is this sort of fuzzy blob at the end here, which represents the quantum uncertainty. This actually shows up if you try to measure this. It shows up as a noise. If you try to measure that signal, you get a noisy value. It's fluctuating due to quantum mechanics. Now what's plotted here is what you get out as a signal when the cavity is in the 0 state in blue, or sorry, when the qubit's in the 0 state in blue, or the 1 state in red. And as you can see, these two fuzzy blobs here kind of overlap. So what that means is that when I go to measure this thing, typically, if the signal looks like this, basically all I try to measure is like how much is the signal along this axis. Is it up here or is it down here? Because that sort of controls which of these distributions it came from. If I find that it's somewhere in the middle, I don't actually know what distribution it came from. I don't know, was the qubit in the 0 state or the 1 state? And in fact, not only do I not know, the universe doesn't know. So I haven't actually really performed much of a measurement at all. Now, if my measurement result was something like this, where I put my cursor now, well, that's much more likely to have come from the 0, the blue distribution, than it was from the 1, the red distribution. So what happens is I actually update the state. Those of you who are familiar with Bayes' theorem, it's basically like a Bayesian update, and there's Bayesian quantum state updating math that goes along with this. But the state sort of goes mostly to 0, but not all the way. And it does so to an amount that is exactly proportional to how confident you are that a point here came from the blue distribution and not the red distribution. Now, if you get a point way up here, it almost certain, or let's say right here, it almost certainly came from the blue distribution and not the red one. So then you fully project the state. But the key is, the weaker your measurement is, the shorter these arrows are, so the more these things overlap. The longer you integrate your measurement for, the less noise you get, because the noise sort of cancels itself out as you integrate. And so the smaller these blobs are, and the less they overlap. So if you want a very weak measurement, you do a very weak probe tone. You don't shine in a lot of light. So these arrows are short. And you don't integrate for very long. You do your measurement over a short time, so these blobs are kind of big. Now, the question is, why do I want a weak measurement? Well, because the measurement has not completely projected the state onto 0 or 1. The information that was there in the initial superposition of the state, the values of these coefficients of 0 and 1, that's actually still there. It's contained both in what the new state is and in the measurement outcome that you got out. Now, here's how they used it in this paper. There's a thing you can do to create what are called Robbie oscillations. You basically drive the qubit with light that is resonant to the qubit energy. And when you do that, the qubit state goes something like this: cosine omega Rabi t times 0 plus sine omega Rabi t times 1. So the qubit state oscillates between 0 and 1. It goes back and forth. Typically, the way we actually draw this is we say the qubit state is a vector onto the surface of a sphere. Notice the Planck sphere. This is just a representation. And we say 0 is up here. Don't ask me why 0 is north. 1 is down here. The qubit state is drawn as a vector that lands on the surface of this sphere. It has latitude and longitude because these coefficients can be complex numbers. So there's actually 2 numbers associated with them. And what Robbie oscillations do is they drive this, oops, make that a different color. They drive this vector in a circle around the sphere. It basically follows a line of longitude around the sphere. Now that's something you can do normally. But what happens when you're doing that and measuring at the same time? Well, what happens is that the qubit gets kicked around. You know, it tries to go this way, but then a measurement says, well, it's in the 0 state, so it gets kicked up here. And then it keeps trying to go, and then you say, oh, actually, it's more likely to be in the 1 state now, so it gets kicked down here. And it's kind of noisy. Now, let me show you what this looks like. Hang on, I have to stop the share for a second. I'm just going to share my full screen. What this looks like is in the presence of a measurement, or indeed in the presence of anything that's disturbing your quantum state. If you do a measurement of these Robbie oscillations, you get this oscillatory signal that eventually just decays away to nothing. And that's because this is an average measurement. We're averaging many, many runs together. And after a long enough time, this thing's been kicked around so much that the phase of this oscillation is completely scrambled. So you're basically averaging just a bunch of completely random things together, and you just get a constant value. So your oscillations are dead. And this is basically an exponential decay of that with some characteristic time. In this case, it's about 3 microseconds or so. Now, here's the thing that they did in this experiment. Let's assume that there's not too much else that affects your qubit, and the only thing that's going to mess with it is your measurement. That's the only thing that's going to cause it to jump around in some sort of random way. Well, if that's true, your measurement tells you exactly how it jumped. And so nominally, you can take that information and feed it back into the qubit and correct that jump. So what they did, let me show you the experimental setup here. Is they took a classical reference signal. Oh, sorry, that's way too small. There we go. They take a classical reference signal. Basically, they take an oscillator just made from a regular computer chip that's just going to give them a 3 megahertz signal. And they say, okay, I want my qubit state to oscillate at 3 megahertz. I want to drive Robbie oscillations at 3 megahertz. Now, what goes on with the actual qubit state, if I plot sort of like where this state, so okay, here's what I want the state to do. I want it to do this. While I'm measuring, what the state actually does is something like this. Okay, well, it doesn't go above 1, but you see, it gets noisy. It jumps around because of my measurement. Now, Robbie oscillations have this nice property that basically the harder you drive the qubit, the faster the oscillation goes. So all they did is they took their measurement signal, which is exactly proportional to this green line, and they compared it with their classical signal, with this white line, with what they were trying to do. And what they said is, okay, if the green line is behind the white line, my qubit is behind in its oscillation. So let me drive it harder and it'll catch up. If the green line is ahead of the white line, my qubit's ahead of its oscillation. So let me back off on my drive and the qubit will slow down and the classical tone will catch up. And when you do this, remember originally you have a signal that looks like this on top here, decays away. You turn this feedback on, and what you end up with is a signal that lasts literally forever. So the time here on the bottom, so this is going, remember this one up here decayed in about, I don't know, 3 or 4 microseconds. This one down here is going for 15 microseconds, and then there's a break just because you can't show all this in one plot. We jump all the way to 980 microseconds, and it's still going. All the way out to 1 millisecond. And in fact, they ran this for like minutes at a time, and it was fine. So what's going on here, basically, is you have a feedback loop that's locked in based on your quantum weak measurement signal. And this was the very first demonstration of feedback based on weak measurement in any kind of solid state system. Now,
is this like accomplishing the same like goal as adaptive optics for like ground-based telescopes?
Kinda, yeah. I mean, it's basically like you have a reference signal. You know what that reference signal should be. And you have a comparator comparing your actual signal to that reference signal. And you're adjusting your, in this case, for adaptive optics, I'm guessing it's the focus or at least some post-analysis. In this case, you're muted. Katie, you're muted.
Thank you. It's made so that as the light comes in and hits the sensor, you've got your correction ready and it goes in like in the moment.
Okay, but it's in software, right?
Yes.
Okay. So in this case, it's slightly different because we're actually controlling the system. It's more like we had a fan up in the atmosphere controlling the atmosphere. It's like, oh, we see, it seems like there's some wind distorting it this way. Let me point the fan the other way.
Oh, okay, cool.
But yeah, I mean, it's a feedback loop. And it's a feedback loop that's meant to stabilize something. In this case, it's stabilizing a dynamic state, an oscillation. Later, people did stuff where they stabilized just a constant state. This one was actually easier for silly reasons. Basically, it's a lot easier to compare something to an oscillation than it is to compare it to a steady value, because steady values have a lot of noise. And that's really it. Now, there's a ton of details that go into this. And in particular, getting to the point where the measurement didn't have a lot of extra noise added to it, where the only noise was the noise that was caused by quantum mechanics. That was really hard. That took years of development. But once we had that, this paper, the result that started this paper, I believe was initially demonstrated maybe 9 months after the first really, really low noise amplifier that allowed this kind of measurement was shown to exist, was created. I did not work on this. I was in the next group, but I heard them be very excited and they made me take a photo of them. This was my grad school lab. So I don't know. I mean, that's the 30-minute version of it. Obviously, there's a ton of details I've glossed over here, but I don't want to just talk this whole time. I think this should be a discussion now. So what do y'all want to talk about?
May I ask a question?
Oh, absolutely.
Yeah. So why is it important to do this for this team? Like what applications, or I guess
It's a good question. I mean, first of all, it's just the answer is because we can. But one thing is that this is sort of the first demonstration of a continuous weak measurement-based feedback. Not a feedback where you like discretely measure the qubit state, you project it all the way to 0 or 1, and then you do something back to it. There's a continuous feedback loop that's running constantly. This has some applications in quantum computing. So these things are quantum bits. They are used for quantum computing, used quite a bit nowadays. But they're not perfect. They have errors. Errors pop up. Basically, the state of the system gets scrambled in a way that you didn't want it to be. Not due to a measurement, but due to other interactions. There's actually ways to counteract this, there's techniques for counteracting this that involve weakly measuring a qubit and feeding back a signal based on that. Now, typically, it's a more complicated type of feedback than this, but this was sort of like the first demonstration to show that it could work. It was also just sort of a nice check that continuous weak measurement behaves the way that people want it to behave, or people thought it would behave, let me say. Because to my knowledge, there weren't actually a lot of good demonstrations of continuous weak measurement at the time. It hadn't really been shown to be a thing. And there were some people who didn't really believe it. Because in Intro to Quantum, you don't learn that. You learn projective measurements. You know, strong measurement. Let me just take a look at the work cited here. I'm trying to say. Come on. Go there. Yeah, it won't go there. Anyway, they're only citing 2 papers for the weak measurement. And I don't think either of those are review articles. And I think one of them is a theory paper. So I don't know if there were actually very many demonstrations here. Just take a look. I'll recognize them. Okay, those are textbooks. Okay, there may have been a few more demonstrations. But this is certainly the first demonstration that it would work in this type of system. Another application is something that my lab is just starting to explore right now. So this is 10 years later. We're looking at trying to implement kind of arbitrary feedbacks. So basically, you measure something, you measure the qubit, or maybe you don't measure whether it's 0 or 1. Maybe you measure the phase of the superposition of 0 and 1. In the language of spin half, instead of measuring sigma x, we're measuring instead of measuring sigma z, we're measuring sigma x. And then feedback something based on this continuously that is completely arbitrary, that does a completely arbitrary thing to the qubit. Not random, determined, but basically we want a way to do whatever, John Q theorist tells me to do. We want the theorist to come up with some interesting set of dynamics they want to look at, and we implement it. This is important because this is a way to simulate what are called open quantum systems. Systems where their interaction with the environment is actually important, and the environment is not well controlled. Because in reality, all things are open systems. There's always an environment. It's not exactly calibrating. It's more like there's a real physical system out there that we don't quite understand, and we want to understand it better. So I'm going to take my really well-controlled, engineered qubit system and make it emulate that physical system. We have good ways for doing that if the thing I want to emulate is a closed system, if it's kind of isolated from its environment. But we actually don't really have good ways of doing it if it's an open system, if the interaction with the environment is important. And this is one way that we can start to do it, because measurement is inherently kind of an open process. The measurement sort of forms an environment that's disturbing the qubit. And then I can have the environment via my control tones also do other stuff to the qubit based on the measurement. For those of you who have taken 438B, basically, instead of trying to simulate the dynamics of a wave function, I'm trying to simulate the dynamics of a density matrix. In density matrices, you don't govern them with the Schrodinger equation, you govern them with what are called master equations. But as always, they did it because it's cool. And let me just check for a second.
What would an example be of an open system that you would be interested in being able to test if you were to get all this stuff to work?
So I can give you answers for like single or 2 qubits, but they won't mean anything because they'll be like, the double excitation Jaynes-Cummings model in the Hubbard model limit. Like that doesn't tell you anything. Let me instead give you the example that we would do like 30 years from now when the technology is just like perfect. A superconductor is a material that conducts electricity with no resistance. And the way it does this, for those of you who 438A, we're going to get to this next week, but 438B has already seen this. Basically, electrons pair up in a superconductor. They form a composite particle. It's known as a Cooper pair. And because that's 2 spin 1/2s, it's a spin 1 or a spin 0, and that's a boson. And so it forms a Bose-Einstein condensate. Anyway, some superconductors, we have a pretty good theory for how this happens. And that tells us how, for instance, aluminum becomes superconducting. This circuit was made of aluminum. Becomes a superconductor below about 1 Kelvin. So it has to be pretty cold. But there's this whole other set of superconductors that are called unconventional, where basically we don't know why they superconduct. The sort of really well-studied theory of superconductivity doesn't explain it. Doesn't explain how you get this pairing of electrons. Now, however it happens, that has to be kind of an open system. The electrons are interacting with their environment a lot. And they are interacting in such a way that kind of thermalizes them. It gets them to some sort of thermal state. But that thermal state is a Bose-Einstein condensate. It's super fluid. It's a super fluid of electrons, so it's a superconductor. If you ever want a superconductor that's going to work at room temperature, it's probably going to be an unconventional superconductor. And it would really, really help to know how those work. Now, I'm not claiming that we could solve that anytime soon. And maybe some theorist will figure out another way to get it in the meantime. Because certainly simulating, 10 to the 23 electrons is going to be pretty hard. But we don't know it yet. Unconventional superconductors were discovered in the early 80s. And we still don't really know how they work. But we really, 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 really want room temperature superconductors, because then you can do all sorts of sci-fi stuff.
I want to ask about qubits.
Yeah.
I'm not too familiar with them. So I have 2 questions. So the first one is, when I was reading the supplement information, I think at one part it says that like it was rotating the qubit about the x-axis, and then the qubit gets attracted to like a plane, like an x=0 plane. So like what exactly, like
Yeah.
I would
So
imagine it as like a physical thing that's like moving around, right? But like I know that's probably not the case. So like how should I?
yeah. So in this case, we're saying rotating the qubit. Really, what we mean is rotating the qubit state on the block sphere. But one way to think about it is if you think of the qubit as a physical spin 1/2, a spin that can only be up or down when you measure it, but then treat it as a vector pointing in space, and you are rotating that spin vector around some axis. So for instance, you start the qubit spin up, which is its ground state. And this is the z-axis. And we say the x-axis is this way. So then we start rotating the qubit around the x-axis, and now it's spin down. And you keep rotating it, and you keep rotating it. Now what the measurement does is it kicks it around as it's rotating. And so you set your feedback back in to lock it back into the rotation, that smooth rotation.
To add on to that, I guess. So is a qubit, does it only have two definite states, or do we only limit it to two states? Because I know the article says like sometimes it finds it in a like a second excited state.
Yeah, so there is exactly one system in existence that only has two states, and that is a true spin 1/2 particle, like an electron or a proton. Everything else has more than two states. But typically you can isolate a couple of them and only consider those. This particular type of qubit, so you got me going now, and you're going to regret it, and I bet you know where this is going if you've taken my class. This particular type of qubit is an anharmonic oscillator. It has a potential energy, which instead of being a parabola, is actually a cosine function. The potential looks like that. And so what you end up with is, in a quantum harmonic oscillator, you would get energy levels that are equally spaced. They're always spaced by h bar omega. Instead, what we get are energy levels where the bottom one's here, the next one's here, the next one is a little bit closer. The next one is a little bit closer than that. The next one's a little bit closer than that. The next one's a little bit closer than that. And it's due to the fact that this is not a parabola, the potential. Now, the fact that these spacings are not the same, that this spacing and this spacing of these energy levels is not the same, means that if I drive at this energy, I only drive that transition. And so nominally, the qubit will stay in one of these states, one of these two. Now, what can happen sometimes is because the temperature is not zero, temperature is finite. Sometimes when you got it up in this state, it can kick itself up into this state. And so that's outside the qubit. You know, it's no longer one of these two states, and it's basically gone outside the subspace that we are considering for this qubit. So it's sort of like your qubit disappeared for a little while. But yeah, for these purposes, we just sort of ignore the higher states. Now, it turns out that anytime this particular type of qubit, those higher states aren't very well separated. Like the difference between this energy splitting and this energy splitting is usually only a few percent. So anytime you want to calculate anything about what this qubit does when it's interacting with some other system, you actually have to talk about like the first 20 levels or so. It's a huge pain in the ass. But for the purposes of the measurement and this experiment, you can basically treat it as having only two states. There are other ways to make qubits out of superconductor that don't have this problem where all the higher levels are like really evenly spaced. There's one type of qubit where the potential energy looks like this. And you basically get one energy level that's like here, another one that's like here, and then the next one is like here. And so it's really easy to tell the difference between this energy splitting and this energy splitting. And it really does act like it has only two states. But this particular qubit that I just drew has its own difficulties. So most people actually use this one. This is what's nice about superconducting qubits, because they're just made from electrical circuits. You can sort of like tweak the potential just by changing your circuit layout.
Can I ask a question?
Absolutely.
I
People just start talking, please. This is not a class.
I apologize if you kind of said this already, I'm not sure, but like, what are the limits of when it says weak measurement? Like, what does that encompass and what?
Yeah, it's actually not, there's no hard and fast rule. Like
are there particular areas where of interest where they're trying to like stretch this concept that it's a bit blurry, or?
I mean, it's sort of like, I'm trying to think of a good example. If I hold up a flashcard that says either 0 or 1 on it, and let's say I have some apparatus that's going to flash it to you very, very fast, okay? You looking at that is sort of a measurement. You're extracting information. Let's say it flashes for 1 microsecond. You didn't see anything. You've extracted 0 information. That is definitely the weakest possible weak measurement. Let's say it flashes for like 10 milliseconds. That's pretty close to like the sort of natural refresh rate of your eyes. You might sort of get some sense of what the number was, but maybe you're not fully confident. That's kind of like a weak measurement. Now, if I hold that thing up for 10 minutes, you definitely know what number it is. That's definitely a strong measurement. But there's no like dividing line here.
But in the context of like applications, I just mean, are there particular areas where it's like especially of interest, and then ones where it's just, oh, this would definitely never apply?
Yeah, I mean, in areas where what you really want to know is like, is this a 0 or a 1? You know, you wouldn't do a weak measurement. You just keep integrating until you became a strong measurement. One of the areas I talked about before was emulating an open quantum system. There are ways to correct for other things affecting your qubit by doing a weak measurement. Something I didn't say before, when Brenda, when you asked about this, and I should have because it just slipped my mind. A qubit is actually like kind of the most possibly sensitive thing that you can create to some interaction that interacts with the qubit, because you can cause the qubit to basically interfere with itself, and you can get it to interfere with itself in a way that's extremely sensitive to some parameter. So one example, for instance, is you can make a qubit out of an atomic transition to atomic energy levels, to electron orbitals. You have an electron transition from one to the other. And for many atoms, the exact energy level there, the exact energy splitting, depends on many different things, but let's say it depends on the magnetic field. So by sort of setting up an interference where you drive the qubit back and forth in a special way, you can very, very sensitively measure the magnetic field. It turns out that there's sort of like a standard limit on this, on how good you can get based on quantum noise. If all you do is sort of the standard technique. But if instead of doing like a hard projective measurement, a strong measurement. You do a weak measurement. And you change your measurement axis. You basically, in this case, you change the orientation of your atom as you're measuring, so that it is going to start trying to line itself up with the field better as you're measuring it. You can actually go far beyond this quantum limit on this standard limit on sensitivity, and get a much more sensitive sensor. So to give an idea, KW Murch here is Kater Murch, who's now a professor at Washington University, and demonstrated this with the superconducting qubit.
Wait, Eli?
Yeah.
I think Katie had a question.
Oh yeah, sorry.
Just like, how did they figure out that it's less sensitive if you measure it while it's trying to line up?
Oh, it's
That just seems like, so was that like just trial and error?
no. So I mean, think about it this way. You are trying to measure, let's say you're trying to measure kind of an arbitrary signal. You're trying to measure a magnetic field that's pointing in an arbitrary direction. And you're trying to measure the field strength. But you don't know what direction it's pointing in. You measure the strength along one axis, and then you go and you measure the strength along the other axis, and you go and measure the strength along the third axis. And that gives you the overall field. But what if instead of doing that, you could just sort of like very quickly line your apparatus up with the magnetic field? Well, then you only have to do one measurement.
Okay, so it's like less sensitive because instead of having to do 3, you just have to do 1.
Well, sorry, it's more sensitive. You can get the same sensitivity in a shorter time.
Oh, okay.
So the idea here is by doing this weak measurement and by tuning your measurement, you're weakly measuring your qubit, and then you're somehow tuning your qubit to be a better sensor as depending on the results of the measurement you get out of it. This can make the qubit more sensitive to some external thing that you're trying to measure.
Mm.
So you go beyond what's called the standard quantum limit on measurement sensitivity.
Wow, so it's already like the most sensitive thing, and then you can make it even more sensitive.
Exactly.
Wow, cool. Thanks.
Eli, can you explain again? Okay, so when we said that we're coupling the qubit with some resonant cavity,
Yeah.
so like my understanding of how we have like that microwave frequency for like the qubit is that that's referring to the energy gap between the ground and excited state.
Yes.
Okay, and then for the microwave cavity, can you explain again what properties about it are like tuned such that it's like the microwave frequency range?
So there's a few different ways to do this. One is actually as a lumped element electrical resonator. I called it a cavity, but it could just be an LC oscillator. This is a capacitor in parallel with an inductor. That is a resonant circuit, which has a resonant frequency of 1 divided by the square root of LC. But you actually get exactly the same math, exactly the same behavior. If you take two mirrors and you try to shine light in between them, you get a standing wave. But the wavelength of that standing wave is quantized because the amplitude of oscillation at the mirror has to be 0. So the lowest possible frequency you can get is you put half a wavelength in. You can also put 1 wavelength or 1.5 wavelengths, etc. But you just sort of pick one of these because these all have different frequencies.
So you just send in something that corresponds to the mode that you're looking for.
Exactly.
Okay, cool.
And basically, let me double check in the actual paper. Yes, it was a 3-dimensional cavity. Okay. They've actually sort of drawn it here. This is the cavity. if y'all can see that.
Mhm.
It's literally like a block of aluminum that they machine a slot into. And that slot sort of like you take that block of aluminum and you take two of them, you stick them together with their slots. And it basically forms like a rectangular box of vacuum surrounded by aluminum. And there's a rectangular cavity mode associated with this, with basically light bouncing back and forth between the walls. Because aluminum is basically a mirror to microwaves when it's superconducting. Let me see actually is there a photo in the supplement? There is not. I will grab a photo. One moment. Here's what one looks like. Oops. Get the actual big photo. Oh, come on. It's bigger than that. Oh, that's really terrible. There we go. Okay. Sorry, my computer's not cooperating. So this is half of the cavity. There's another half that goes on top of this that basically looks like the same, just mirrored. And you can see sort of this is just an empty hole. So when you put another one on it like this, you get this empty cavity that's sort of filling this space. And what's plotted here is actually the electric field that you get from driving this cavity. So you can see it's strongest in the middle and it sort of dies as it gets to the edges. And in this case, I believe the field is actually oriented sort of up and down. In this case, it's kind of going this way. But that's the lowest resonant mode. And you put your qubit circuit just in the middle there. Like this. These are useful slides. This is what the qubit looks like. And it sits right there. This whole thing, is not particularly compact. It's maybe about that big, a couple inches or so. Fun fact about this. This is known as the 3D transplant. This was invented in like 2011. And it made the coherence of these qubits, the length of time that they can go before they get scrambled by the environment, way better, like 10 times better. Sometimes 100 times better than what people were doing at the time. It solved a bunch of problems. It's bulky, and basically using lessons from this, we've gone back and made the sort of more compact circuits just as good. But this was really a huge breakthrough. And in particular, one thing it did is it showed that the little circuit element that's circled here, which I won't get into, was not the problem that we were facing. Now, my PhD project was based on the assumption that this circuit was the problem, that this little element was the problem, and that I was making an alternative to it. Approximately 1 month before this result was published, I discovered a terrible, terrible property of my alternative to this little circuit element that made it completely useless for this purpose. And then 1 month later, Hani Pike, who is extremely nice, and she's great, she's working at IBM now, but she published her 3D transplant result that showed that really not only was I taking the wrong approach, but there was no reason for me to even do that project to begin with. But silver lining, my device was so bad because it had this terrible interaction with a particular type of thing that occurs in the environment. And what do you do when you have something that interacts really, really strongly with some environmental mode?
Use it as a detector.
Exactly. So now I have a really good superconducting quasi-particle detector. that I think a bunch of you know James Farmer, my group. Yeah, so that's his PhD project. He's working on that.